Good morning, everyone. My name is Keshav Bharadwaj, and I'm a PhD candidate at Oregon State University, working with Professor Jason Weiss and Professor Burkhanishkar. The topic of my talk today is a Monte-Carlo-based thermodynamic analysis on the performance of calcined clays in cementitious systems. So far in this session, we've heard a lot about the production of calcined clays, the impact of the method of production on the reactivity, as well as the performance of concretes and other cementitious mixtures made with calcined clays. In this talk, we will address the following questions. What makes calcined clays unique as a porcelain? How can we exploit this uniqueness to increase the limestone content in cements when we use calcined clay? And how do we consider the natural variability of calcined clays to increase the limestone content in cements further? So first, let's look at what makes calcined clay unique as a porcelain. The plot on the left is a ternary plot of the chemical compositions of different SCMs. That is, their silica, alumina, and calcium contents are plotted. The blue diamonds over here are the calcined clays. As you can see, the calcined clays lie very close to the silica alumina line, and that's because they have a high silica and alumina content. Typically, their silica plus alumina content is greater than 80%. Calcined clays are also unique among porzolans as they have a high alumina content along with their high silica content. The alumina content of calcined clays is typically higher than other SCMs like fly ashes, silica fumes, or slags. Another reason why calcined clays are unique is because of their reactivity. We can use the pozzolanic reactivity test to measure the numerical value of reactivity of the calcined clay. In the pozzolanic reactivity test, the SCM is mixed with an excess of calcium hydroxide and water in an alkaline medium and allowed to react. The calcium hydroxide consumed by the pozzolanic reaction and the heat released by this reaction are plotted on a heat released versus calcium hydroxide consumed plot. The value of reactivity is then calculated by interpolating between the heat released and CH consumed by pure silica, as well as the heat released and CH consumed by pure alumina. For example, this particular fly ash would have a reactivity of around 20%, and this particular calcined clay would have a reactivity of about 80%. So what we find is that the reactivity of calcined clays is on average higher than other conventional SCMs like fly ash. If we look at the results of the pozzolanic reactivity test on this plot, the fly ashes have reactivities between about 20% to about 50%, while calcined clays have reactivities between about 45% to almost 95%. And the mean reactivity of the calcined clay is about 70%, which is significantly higher than conventional SCMs like fly ash. So this is the first takeaway from this talk. Calcined clays are highly pozzolanic materials. They are unique in this aspect as they have high amounts of reactive alumina along with the silica, and they have a very high reactivity, with their average reactivity being about 70%. Now let's look at how we can exploit this uniqueness of calcined clay. On this slide, we have two plots of porosity as a function of the limestone content in the cements used for different mixtures. The y-axis is the porosity of the paste, and the x-axis is the limestone content in the cement used. And the porosity is calculated for varying limestone contents for different mixtures. As limestone is added to the mixtures, typically the porosity drops and then increases. But I'd like to draw your attention to this point where the porosity is the same as the porosity when you have no limestone in the system. So for a typical neat PLC system, this would be around 25% for this particular PLC, where you can have about 25% limestone, where the porosity is the same as when you had no porosity in your system. For siliceous systems, the presence of silica typically doesn't impact this equivalent porosity limestone content. And this value of limestone that you can add is close to a system without any SCM, about plus or minus 3% limestone content as for a neat PLC system. If we look at a system containing alumina, however, which is the plot on the right, we can immediately see that as alumina is added to the system, the limestone content in the cement can be increased without decreasing the performance of the system. The equivalent porosity limestone content can be increased by about 5 to 7% with just a 2.5% addition of reactive alumina to the mixture. So this synergy between alumina and limestone is very useful as we move to cements with higher limestone contents. And this is useful in practice as increasing the limestone content in cements has a direct impact on reducing the carbon emissions from concrete. I would like to note at this point that there are several state highway agencies that are asking if potent limestone cements or ASTM C595 type IL cements can be used as direct replacements for ordinary Portland cements or C150 cements when SCMs are used. And this study helps answer that question. If we use SCMs that are rich in alumina, especially like calcined clay, the limestone content in the cements can be increased while maintaining the performance. For example, the plot on the right is again a plot of porosity as a function of limestone content in the cement. And when you have increasing contents of calcined clay, the equivalent porosity limestone content can be increased. And this increase is about 5% increase of limestone in the cement for every 5% of calcined clay added, approximately. So this is the second takeaway from this talk. When alumina-rich SCMs like calcined clays are used, the limestone content in the cements can be increased while maintaining the performance of the system. This is because alumina reacts with the limestone and improves the performance of cement plus limestone systems. And a higher limestone content in the cement means a lower carbon footprint of the concrete produced with the cement. So we want to explore this synergy between calcined clays and limestone further so that we can move to cements with higher and higher limestone contents. However, calcined clays show a wide range of chemistries and reactivities. If you recall from a few slides ago, the reactivity can be anywhere between 45% and 95%. Experiments are slow and limited. So what we can do is we can use a Monte-Carlo-based thermodynamic modeling framework to explore the calcined clay limestone synergy by running hundreds of thousands of simulations to capture the impact of the natural material variability on the performance of the systems containing calcined clays. For example, this plot that I had shown you in the previous slide is for one particular composition of cement, as well as one particular calcined clay, which has a specific composition and a specific value of reactivity. So these slides show the statistical data obtained from the literature for reactivity and composition. On the left are box plots of reactivities of calcined clays, as well as some other conventional SCMs. In general, the calcined clays have a higher reactivity than other conventional SCMs like fly ash or slag, but they do show a wide range of reactivities ranging from 45 to almost 95%. The plot on the right is a box plot of the composition of calcined clays obtained from the literature. And this plot is intended to show the range of compositions of calcined clays available. So the silica content, for example, can range anywhere between 45% up to 70%. The alumina content can vary anywhere from 15% to 45%. And this is important since the alumina content is important for the calcined clays synergy with limestone. And hence, it's important to study the impact of variability of the reactivity and composition of the calcined clays on the performance of cementitious mixtures when you're using calcined clays in them. So to study the impact of variability on performance, we need to predict the performance. And to predict the performance, we used a modeling framework developed at Oregon State University called the pore partitioning model. The inputs to the model are the OPC amounts and chemical compositions, the SCM amount and chemical composition, as well as the maximum degree of reactivity of the SCM measured using the Porcelainic reactivity test. These inputs are run through a kinetic, thermodynamic, and pore partitioning model framework, and the outputs of the model are the reaction products and the volumes of pores. And these can be scaled up to concrete to predict the performance of concrete in terms of its strength, porosity, formation factor, resistivity, etc. For this talk, I've limited the scope of the performance to porosity, but we can also predict other performance parameters like strength, formation factor, etc. So on a slight yet technical tangent, I would like to note that it is important to use the right CSH model when you're using a thermodynamic modeling framework. There are different types of CSH models available in the literature, and especially when you're trying to model an OPC plus calcined clay system, there is a need to understand what is the most appropriate CSH model to use. This is because the major components of calcined clay, which are silica and alumina, react to form calcium silicate hydrate and calcium aluminate silicate hydrate phases. This pozzolanic reaction causes the pore refinement, which changes the pore volumes, as well as improves the strength and transport properties of concrete. Adding calcined clay also decreases the calcium to silica ratio and increases the uptake of alumina and the calcium silicate hydrate. So it's very important to use the right CSH model from the thermodynamic databases that are used. So to the best of our knowledge, we're the first group that has implemented and automated this selection of the right calcium silicate hydrate model algorithmically. What essentially that means is that we can switch between the CSH models automatically, and we can select the right CSH model to use for the right mixture composition without any need for experimental input. So apart from the tangent, let's get back to the modeling framework, where the inputs are the chemical composition of the OPC, the amounts and chemical compositions of the SCM, as well as the reactivity of the SCM. We can randomly generate these compositions and reactivities from the statistical data from the literature using probability density functions. And with this framework, we can run millions of simulations to understand the role of the material variability. So as an example, on this slide, I'm showing two plots of the probability distributions obtained from the literature, which are the lines. This is for alumina content in the calcined clay, and for the plot on the right is for the reactivity of the calcined clay. The lines are the probability density functions obtained from data from the literature, and the histogram is the generated data points. In all cases, as you can see, we generate a statistically significant number of data points so that we can capture the natural material variability. For example, in this case, I think we've run about 100,000 simulations per mixture. So now let's look at the results of these simulations. The plots on this slide are a function, porosity as a function of the limestone content in the cement for a neat PLC system, a PLC system with about 10% calcined clay, and a PLC system with 10% fly ash. The bold line in all of these plots in the center of all the regions are the mean predicted porosity at a given limestone content for each mixture. And the shaded area represents one standard deviation of porosity that is predicted away from the mean. So the modeling shows that even when we consider the natural variability in calcined clays, the limestone content in the cements can be increased by about 10%. For example, in a neat cement system, the limestone content that can be added to the cement while considering the variability of the cement itself can be anywhere between 10 to 20% without affecting the porosity. When 10% calcined clay is added to the binder, the limestone content in the cements can be increased to 20 to 35%, which is about 10% higher than in a system without any calcined clay. And this includes the natural variability of cements and calcined clays that are produced. This 10% increase in calcined clay is made possible by the addition of calcined clay, and it's significantly more than when a conventional siliceous SCM like fly ash is used. When fly ash is used, the limestone content can be anywhere between 10 to 20%, which is similar to the range of neat cement system without any SCM. However, when you add calcined clay, you can increase the limestone content in cements by about 10% because calcined clay has reactive alumina that can react with the limestone to improve the performance of the cements. So to conclude, the three takeaways from my talk are that calcined clays are unique SCMs as they're highly pozzolanic with a large amount of reactive alumina. This uniqueness can be exploited through the synergy of limestone and alumina, and adding calcined clays to concrete enables us to increase the limestone content in cements, which can lead to a lower carbon footprint of the concrete that's produced. The Monte-Carlo-based technique shows that even when you consider the natural variability of calcined clays available, the addition of calcined clays allows for an increased limestone content in the cements used. So with that, I would like to thank everyone for listening to this talk, and also a big thanks to our financial sponsors, ARPA-E, the National Science Foundation, the California Department of Transportation. I would also like to thank professors and graduate students from other universities who are involved in some of the projects for their feedback and insightful questions and comments along the way, specifically Penn State University, Purdue University, and the University of Texas at Austin. And yeah, with that, I thank you for your time. If there are any questions, please drop them in the Q&A box and I'll be happy to answer them.
Thank you so much, Keshav. There is one question in the chat or in the Q&A box. The question is, what is the water cement ratio used for pastes in the porosity?
So right now, I think it's 0.42, if I'm not wrong, because we wanted to simulate at a later age when, yeah, where we had, sorry, that doesn't answer the question, but yeah, it's 0.42.
Okay.
It's 0.42.
Fantastic. Fantastic.
Yeah.
And there's another question. I'll do this one out loud too. That why is the porosity drops at lower limestone content, LS content? Also in reactivity tests, there was no alkali sulfates. Did you consider any sulfates?
Both are excellent questions. I will start off with the porosity dropping with limestone. Well, when you don't have any limestone in your system, essentially the phases that you have are monosulfates, which contain some amounts of gel water as they release water when you heat them up to 100 degrees Celsius. As you increase the limestone content in cements from 0 to about 2%, the presence of limestone stabilizes ettringite and causes the formation of carboaluminates. Both of them are space-filling phases that lower the porosity. Above a certain limestone content, however, there's no more reactive alumina in the system, so the excess limestone dilutes the system and increases the porosity. That's exactly why when you have more reactive alumina in the system, the porosity decreases further and you can add more limestone to the system because you form more ettringite and more carboaluminates. Now, as for the question on in the reactivity testing, why we don't add sulfates and carbonates, well, the purpose of the pozzolanic reactivity test is to determine the numeric value of pozzolanic reactivity. So typically in the reaction products that you form when SCMs react with calcium hydroxide, the silica reacts to form calcium silicate hydrate and the alumina reacts to form calcium aluminate hydrate. When you add sulfates and carbonates, you change the reaction products that form. So essentially, silica doesn't react with the sulfate, but alumina does react with the sulfate preferentially to form monosulfates rather than calcium aluminate hydrates. And this reaction changes the heat released and the calcium hydroxide consumed and even the bound water, if you will, of the resulting mixture. So the chemical composition of the SCM will impact the output of the results. Whereas if you don't add sulfates or carbonates, you can directly interpolate the reactivity between these two lines and you can get a numeric value of reactivity. So yeah, to summarize the answer to the second question, you're changing the phases that form when you add sulfates and carbonates. So we don't recommend adding sulfates and carbonates if you want a numerical value of reactivity.
Fantastic. That was a very clear and important response. Thank you.
Thank you.
Thanks, Keshav.